I think we should begin. Can everyone hear all right? Okay. So I noticed that food ran out a bit for lunch. We're compensating for that in two ways. One way is we're ordering more food. And the other way is I want to mention that there are 4 kinds of people in the world. Right. Okay, so there's 4 people. There's those who paid for the learning summer school, and you know they're paying for their food. This goes those who we gave financial aid to, and we paid for their food. So what this lecture is about is how to avoid inventing a new learning algorithm for every learning problem. It's a very common kind of thing. People, like, ooh, I have a new learning problem. Let's invent a new learning algorithm. But maybe we can avoid that, and maybe it's beneficial in a lot of ways. If you have questions during this talk, you should feel free to ask them as they come up. I kind of like things interactive, or else I have this feeling that I lose everyone. Okay, so learning problems. There's a lot of different kinds of learning problems. There's sort of binary ones. Is it raining outside or not? There are cost-sensitive ones, like which commute is faster. A number of people are actually commuting. Some people claim that they're commuting 2 hours per day to see this talk. And wow, I couldn't do that. But if you're commuting, you have a choice of different paths you can take, right? There's different routes available, and you want to choose the path which kind of minimizes your time. It's a cost-sensitive classification problem. And then there's issues like which stock will go up. It's a favorite. And can I make the light before it turns red? Right. So, stopping early is okay because the penalty's not that bad. You lose a minute or two. But if you go too far, well, that's very bad because you get rammed. So it's an importance-weighted classification problem. Okay. Different kinds of learning problems. And then reductions are about how we can solve all of these with the same learning algorithm. So you can ask questions. So a reduction takes one type of learning algorithm and turns it into a different type of learning algorithm. So it solves a different type of learning problem. You can ask questions like, how do I solve importance-weighted binary classification with a classifier? How do I solve cost-sensitive classification, or reinforcement learning, or regression? There's many different kinds of learning problems. And one thing I should mention is, although I'm going to be talking about reducing things to a classification, it's easy to imagine using another primitive, like, say, regression. Okay, so before I start into, the grinding math and all, maybe we should feel a little bit motivated. And these are the basic four reasons why you want to play with reductions in learning. So I'll go through each of these individually. Okay, so there's these binary classifiers, which just decide between 2 possibilities. And there are the multi-class classification problems. So one of the approaches that people do to solving multi-class classification is one against all. So they create a bunch of binary classifiers, one for each class. For class I, the binary classifier is it class I or not? Is it class J or not? Is it class, 1 or not, 2 or not, whatever. And then at prediction time, what happens is you evaluate, if you have k classes, then you evaluate all k classifiers. And if only one raises his hand, then you say, it must be this guy. And if 2 of them raise their hands, then you say, I'll just randomize between the 2. And if none of them raise their hands, then you just kind of randomize amongst them all. You don't have any information. Okay, so that's one against all. And then if you go and you analyze the mathematics of this, what you discover is that this failure mode is significantly less severe than this failure mode. Because you still have an even chance of picking the right guy in this kind of failure mode. But the odds of picking the right guy when this happens are much worse, like 1 over k. So you can take advantage of that, and you can create, instead of reducing to binary classification, you can reduce to importance-weighted classification, so that the importance of raising your hand when you're supposed to is larger than otherwise. Then you can reduce that to binary classification, and you can compare these two methods. And it turns out that this weighted one against all is just always better. Right, so this is the accuracy. So things above the line are wins for weighted one against all. This is a bunch of different learning algorithms on a bunch of different data sets, and I guess one time we did slightly worse, but every other time we did better, sometimes significantly better. So there's some motivation in terms of working. And then another motivation is sort of code-wise. Reductions are sort of inherently modular. We do not peer inside of the workings of a learning algorithm, so we do not need to. Yes?
A priori, how do you know you want to reduce from one versus all to weighted one versus all?
It's not reducing from weighted one. That's not the reduction. The reduction is from multi-class classification to binary classification. Does that make sense? So we're reducing from multi-class to binary, and you can do it sort of directly with this one against all, or you can go from multi-class to weighted, importance-weighted binary, and then to binary. So I was comparing this to this.
So the importance weighted is less of a reduction of binary, is that right? It's more like tweaking parameters of the given algorithm? Or no?
The importance weighted binary, there's no tweaking parameters of algorithms. So all the reductions that I'm talking about are black box reductions. You can apply them to any classification algorithm, and you can apply them given some standard interface to all classification algorithms. There are no special parameter tweakings or anything like that. So I was comparing this direct approach for doing one versus all to weighted one versus all, composed with something I want to talk about later, which is this costing reduction. Yeah?
You brought up as an example of why reductions work. Would it make sense to compare the reductions? So you compare two different reductions to each other. Would it make sense to compare to a multi-class classification algorithm and see that it actually does this as well?
Yeah, I agree. So one thing which is important is that reductions are not competing with themselves, right? I mean, these are two different reductions. The one versus all and the weighted one versus all composed with this costing. But what you really want to compare with is other ways of doing multi-class classification, right? Because you want to say this is the best way. And that comparison is not done right here. It's done for some of the other things I'll present later. Okay, so modularity. Right. No parameter tweaking. We're just thinking about the classification algorithm as something with a particular type. And we're just using it as you would use things with that type. We're not actually fiddling with any parameters in the classification algorithm. You can reuse your old learning algorithms via these reductions, right? So that's kind of nice from a not having to think so much viewpoint. In particular, I think there are maybe there's 50 classification algorithms that have been invented. which is pretty impressive because I'm not certain there are 50 public data sets. But if you can form a reduction to classification, then you have 50 algorithms to apply to whatever learning problem you have. It takes a while to come up with 50 algorithms. And then, yeah, you can actually, in addition to using old learning algorithms, because it's entirely black box, you can use your old code. Just a matter of matching up the interfaces right. Okay, so right, this is sort of a research motivation. What is reductionism? Reductionism is figuring out how to cut your problems into small problems and then solve the small problems and then compose them to solve the big problem. And one of the reasons why it's kind of an interesting direction to look research-wise is because this approach has worked extremely well at certain times in the past. So in particular, computations are kind of reduced to a transistor, if you think about it. Just do one very simple computation and, compose it the right way, and, ooh, look, it's an opteron. And people are getting very good at rendering scenes. The basic element of rendering is rendering a triangle or maybe a very simple polygon. And then actually much of science kind of follows this reductionist approach. So you take some, you try to figure out how to predict the most elementary things, and then you sort of compose these predictions to figure out where the spaceship goes and so forth. Okay, so the last thing is that it's actually pretty easy to use. So you figure out what the type of your learning problem is. This is something that you always need to do. And then maybe you can find some pre-made reduction from your type of learning problem to whatever learning algorithms you want to apply. And then you just compose these things, throw in your data, and you get a predictor for your learning problem. Maybe this is a bit easier than other approaches, which, so what are two other approaches? Another approach is to just invent a learning algorithm to solve your B-type problem directly. We have Zubin Garamani, who is a very good Bayesian, coming on Friday, I think. And he will tell you that the right thing to do is to figure out a prior over the different data generating distributions for B, and then take the prior, update with Bayes' law to get the posterior, and so forth, right? But maybe specifying the prior is a little bit difficult. It can be a little bit tricky at times. Maybe this is an approach which lets you just try something quickly, and then if it works, great, and if it doesn't, then maybe you need to sit down and think a lot more. So what I'm trying to say is that this is sort of a reasonable first pass approach on any particular learning problem. Okay. So we're going to be reducing to classification. And maybe it's worthwhile to specify exactly what I mean by classification. So these are pretty standard definitions. You have the classification problem is defined by some measure on x cross 0, 1. So think of D as a probability distribution. You can draw an example of an x and a y pair. The y is just going to be 1 bit. And then a classifier is something which just maps from this feature space to that 1 bit. And then a classifier learning algorithm is going to be given some examples. And it's going to try to find a classifier, which is a small error rate. So the error rate is the probability that under a random draw from D, the classifier is wrong. You want to minimize the error rate. So one thing which is very different about this analysis from some of the other things you see is that we are not assuming that the data is drawn independently and identically. So maybe this is something which seems kind of esoteric, but this is actually a pretty important thing. The reason why it's important is all the analysis that I'm going to tell you today applies to every learning problem of some particular type. Because you can always say there is some measure producing some test example, right? And since we're not actually going to assume that the training set is drawn from the same distribution, this will always apply. Yes?
Are you assuming it's still IID from something?
No. So I guess we can always say that for any particular test example, there is some distribution that you draw that from. Now, this distribution may be entirely dependent. It may be actually deterministic. You just draw all the weight is on one particular example. But there's always some process producing that test example. And that is the process that we're actually going to be analyzing. It's kind of, well, it's interesting that you can analyze this at all. You'll see why it's possible later. Are there any questions about the basic setup? The only thing that's tricky is we're not assuming IID data. Okay. So this is the outline. I'm going to go through 4 reductions. One of them is from importance weighted classification to classification. So that's this one over here. Another one is from predicting the class probability to predicting the classifier, just predicting classification. Another one is from multi-class classification to classification, which is this. And another one is from cost-sensitive classification to classification. So this gives you some range of tools and should hopefully give you some idea of how this all works. Okay. So importance weighted classification is very much like classification, except you have importances that your distribution is over, right? So in addition to drawing a feature and a binary prediction, you draw some importance. And then you still are trying to find a classifier, which is a binary predictor. You are given an importance-weighted data set, and your goal is to minimize your importance-weighted loss. So if this I was gone, then it would just be a probability distribution. So it would be the same as previously. So if I is always 1, we're just minimizing error rate. But if I is varying, then we need to write out the probabilities and expectation. And we're looking at the expected importance-weighted errors. So this is the stoplight example. The error rate, or the importance of stopping too early, well, doesn't matter that much, right? But the importance of stopping too late, that could matter quite a bit. I should mention one thing, which is that I just put the slides all online, which means everybody who really likes taking notes, you can continue, but they're online. Okay, so there's a basic core theorem, which is sort of folklore from decision theory. And this is that you can turn this importance-weighted problem into just an error rate minimization problem. And it has to do with sort of renaming the probability distribution. So I guess the claim is that for every classifier, for every importance-weighted distribution, if you form this other distribution, which is just kind of reweights the examples by the importance, then the importance-weighted loss equals the error rate of this new distribution times this normalization term. And that's a very simple example of a reduction, because it says that if you minimize your error with respect to d, then it's equivalent to minimizing the importance-weighted loss with respect to d sub I. And the proof is it's just very simple. Just a matter of kind of unwinding the definitions. So in particular, we have our importance-weighted loss. And then I can write out the expectation as a sum. So we have the I here. And then this d is I times d sub I. So then we just get the d. Then we have the normalization term, which comes out. And then this is just an expectation of an indicator function, which is a probability, times this normalization term. And that probability is just the error rate with respect to d. Right? So this is the simplest version of reduction. So we should make sure everyone gets it. So this theorem says that if we can optimize our binary error rate with respect to d, that's entirely equivalent, up to some normalization term, to optimizing our importance-weighted loss. That normalization term, by the way, has to be there. So if you took all of your importances and you doubled them, you would expect your importance-weighted loss to double. Yeah? Okay. All right. Right. So maybe we should. Thank you. So this notation says that expectation with respect to x, y, and I drawn from d sub I. All right. So this is the expected importance. And this, okay. For probabilities, this is x and y drawn from d. I'm just ignoring the I. Yeah? It's just one distribution d sub I. So I guess the claim is that having one distribution d sub I is sufficient for any problem where you care about this kind of thing. And the reason why it's sufficient is because we're not actually relying upon this IID stuff. So there's only one example we need to care about, the next test example. Because there's only one example, there's only one distribution that example is drawn from. Okay. So that's a basic theorem. Then there's a question left, right? The question is, how do we use this basic theorem for our learning algorithms? So the way that you can shift from one distribution to another is using rejection sampling. So the way that rejection sampling works is you pick some constant, which is larger than all the importances. Whoa. That was pretty impressive. You have such power there. And then for each sample, you're going to flip a coin with a bias of I over C. Right? So this is less than 1. And if the result is heavy, you keep it. And otherwise, you throw it away. Okay, so this is some distribution to another. And you can prove that samples drawn from d sub I and then using this process are actually drawn from d. So there's actually a lot of other methods which come to mind when I first tell people this. For example, they talk about duplicating examples and so forth according to the importances. And although that core theorem did not rely upon independence, it is certainly the case that many of our learning algorithms rely upon independence in the data set. So you will be unhappy if you do tricks with duplicating examples or even sampling with replacement. I don't want to go into what that is exactly, but you'll be unhappy. And the reason why you'll be happy with this and unhappy with these other approaches is that rejection sampling actually preserves independence in the data. So this is something which the theorem does not tell you to do, but because our learning algorithms have this weakness that they really rely upon IID samples, it's a good idea to try to preserve independence in your reduction. But there's a drawback here. Oh, you have a question?
So you do this only once? Or
Right. Exactly the drawback. So the drawback here is that you end up throwing away a lot of your samples, especially when your importances vary a lot. So doing this once is what the theorem motivates, but maybe what you want to do in practice is sort of do it multiple times. So you can rejection sample multiple times from this S sub I, and then you can learn some classifier, and then you just use a majority vote over these classifiers to make a prediction. Is that the same as what? Yeah, so AdaBoost also does a majority vote. A lot of learning algorithms, a lot of meta learning algorithms end up doing majority votes. And you can think of a lot of learning algorithms just themselves as doing majority votes. So predict according to the majority vote is a very common mechanism in learning. Say again? Right. So in AdaBoost, this is all going to be talked about in much more detail when Rob Shapiro visits. But AdaBoost, the way it works is it's also sort of a reduction. It's using an Oracle learning algorithm. And what happens is you feed your Oracle learning algorithm importance-weighted data. And there's a problem of fitting that to classification. And one way to do that fit is actually to use rejection sampling. That's right. And I understand that actually works pretty well amongst the different possibilities. Another approach people often use is they try to tweak the learning algorithm directly to take the importances into account. And my impression is that that's no better in practice. Yeah?
So with that, you also rejection sample and just have one big sample to the
Yeah, that would be dangerous. The reason why that would be dangerous is because you lose this independence that you're trying to preserve. So if you take each of these individual S's and you union them together, you concatenate them together, then it's quite possible to end up with the same example twice. And the process of drawing from D sub I and then rejection sampling could be of the sort where there's just no probability of having the same sample twice.
You're assuming it's not you know what I
So you have to kind of keep straight what the theory motivates. Maybe I'm not keeping that straight. The theory says you can do any method of transforming distributions you want. As long as you transform to the right distribution, you're golden. But in practice, what happens is your data really likes, your learning algorithm really likes independent data. And because your learning algorithm really likes independent data, you want to try to preserve the independence if it's there. Okay? All right. Basic algorithm, very simple. In fact, dead simple. And there's an interesting thing about this algorithm. it actually works pretty well. So there was some contest. So this KDD Knowledge, Decision, and Data Mining Conference has various prediction challenges. And in 1998, they had some prediction challenge, which was an importance-weighted prediction problem. I think it was a spam optimization problem. So you're working for a charity. You want to send out flyers saying, give us money. But you don't want to send out too many flyers because their flyers are expensive. So you need to somehow predict who's going to give you money if you send them a flyer and who will not. And then in the ideal case, you can just send flyers only to people who will give you money. So the standard way of trying to measure this is in terms of profit. This is where the winner was. And if you use that very simple piece of code, with naive Bayes you get here. With boosted naive Bayes, you do as well as the winner. With a decision tree, you actually do a good bit better. And with a support vector machine, you're still a little bit below the winner. Yeah?
So do you ever run into problems where you have to rejection sample so much that you essentially made the problem say NP complete or something?
No.
Why?
Do I ever run into problems where I rejection sample so much that the problem can be complete? Why do I not?
I mean, it seems like you could get really unlucky and you would have to sample an exponential number of times before you get what you're looking for.
I think it's worse than that. You could get really unlucky, and you could rejection sample until your data set is so small you just can't solve the problem. So your error rate will always be 0.5, no matter what.
So is there some way to classify what kind of transformation leads to that problem?
Anything which throws out data could lead to that problem. So basically the issue is, if you rejection sample and you get a smaller data set, does that mess you up sometimes? And the answer is certainly yes. So my favorite example of how this can mess you up is if you're trying to learn, so the function that you're trying to learn is a parity of a subset of your bits. So you have a bunch of bits for your feature space, and you want to learn a parity of the subset. Then the number of samples you need, information theoretically, is equivalent to the number of features. It's the same as the number of features. Because the way that you solve this problem is you try to just do Gaussian elimination, and then you can figure out what the bits are. So if you lose one sample there, you're hosed. But it seems that in practice, that's not the way learning problems really are. So in practice, this seems to work pretty well. Okay, so some reasonable performance. I think we can assume that basically every method was tried on this. The only thing which is not highly convincing about this is that we didn't do it in 1998. Right? We invented this later. But it's hopefully a little bit compelling because it's a very simple algorithm which uses sort of a tried and true technique and does reasonably well. Okay, so that's how you go from importance-weighted classification to classification. Any questions about that? Okay, so the next one is a bit more interesting. You want to go from class probability prediction to classification. So you're trying to predict, so here's the definition. It's the same, the definition of the problem is the same as for classification. But now we're trying to make a probabilistic classifier which predicts some value between 0 and 1. And trying to minimize our error rate, we try to minimize our squared error. Right? So if the actual probability of 0 was 0.5, given some particular x, we would want this value to be 0.5, because that would minimize the expected value here. if you think about this right, you realize this is also regression. At least it's a special kind of regression. It's a kind of regression where you always observe zeros or ones, and you want to try to predict the probability of 0 or 1. Yeah?
Which is y as the log of CP plus
Yeah.
1 minus y and the log of 1 minus c.
Yeah. So this is like regression, but it is fairly common to use the log loss. So the way log loss is defined is maybe log of 1 over the probability of the class that actually the probability that you predicted of the class that you observed. Just a minute. So log loss is pretty interesting, and the reason why it's particularly interesting is because it's unbounded. And because it's unbounded, it turns out you can't do it in this framework. There's a fundamental difficulty, and the fundamental difficulty is that unboundedness, exactly. So if you have a classifier which exercises the full range of values, there's no way to actually form a reduction in the kind of framework that I'll tell you. You can easily avoid that. You can have your classifier clip to where it only predicts things between 0.1 and 0.9. And then everything is bounded, and then it's possible. But the story is not so nice when you want to do log probability.
You can do it between 0 and 1 without taking 0 and 1.
If you, arbitrarily close to 0 is still pretty bad. You can still be pretty large. All right, you had a question?
So are you here just trying to predict posterior probabilities?
Yeah. You can think about it that way. One way to think about this is, here's a technique for taking any classifier learning algorithm and extracting a classifier probability, a posterior probability, which is maybe not so obvious that you can do when you're just predicting either 0 or 1, not something in the interval. Yeah?
So you want your CP to be P of X given Y? That's what your goal?
Yeah.
P of Y given X, I'm sure.
P of Y given X. Right.
So why isn't your cost CP of X minus P of Y?
All right, good. So the reason why my loss is this is because I can observe these and I can compute this. But what you really want is to say that this minus the actual probability is small, right? And there's a kind of a cool, which is that these are equivalent up to some additive constant, right? And that additive constant is there for every classifier. It's the same constant. So roughly speaking, the constant is, if you plug in the probability of minus the actual observed y squared, take the expectation, it's the constant. It's independent of c, and that's the only difference between these two things. Okay, so that's the problem. And then maybe we want to think a little bit about why we want to do probability sometimes. Because, there's a lot of situations where you don't want to do probabilities. You want to make some particular prediction, and you want to that prediction tells you what you to do, and you either do it or you don't do it. But there are times when probabilities are kind of required. One of them is when you're talking to a doctor. Maybe the doctor doesn't want to be unemployed, so he would prefer that you actually tell him probability. He makes judgments about what to do, rather than having the classifier just tell the doctor what to do. And then another situation where this comes up is sometimes you have a lot of data sources which are spread out all over the place. And maybe it's expensive to communicate between these different places. So you want to summarize sort of the probability of y given x from each of the individual sensors. And then somewhere later, you want to fuse them. So instead of transmitting all the information from every location to one location, you can just transmit maybe the probability from one location to the central location. And that can be arbitrarily cheaper. Another reason why this comes up is because you sort of want compatibility. You want to think about, here's one component of the system, it's using some sort of Bayesian technique, and here's some other component of the system, it's using some sort of classifier technique. And now maybe you want to extract some sort of probabilistic prediction so that you can kind of fuse things in the right way. Okay, so there's some reasons. And then how does this technique work? So I'm going to call this technique probing. So there's a basic observation that starts things off, which is that if you have a perfect classifier, and that perfect classifier says 1, that's saying the probability of y equals 1 given x is greater than 0.5. And you go, that's interesting. What if I pick some uniform random variable between 0 and 1, and I make this importance-weighted transformation? Right? So I can create an importance-weighted data set, and the importance will be this y minus p. So if y is 0, then it's p, and if y is 1, it's 1 minus p. And then you can think about that a bit, and you'll realize that if your classifier for this importance-weighted transformation is perfect, that implies that when classifier says 1, the probability of y equals 1 given x is greater than p. So here's a particular, this is a proof in one table. So if the prediction is 0, then the expected, so the importance is going to be p, and the probability of 0 is minus probability y equals 1 given x. And when the prediction is 1, the importance is 1 minus p, and the probability of y equals 1 given x. And these two are equal when p equals this probability of y equals 1 given x. And there's just a matter of checking the sign, which works out. It has to work out because we thought about that case first. Yeah? Yeah, well, for this analysis, it doesn't even matter. You can just pick it however you want, 0.3, 0.2, whatever. And then this analysis holds. This statement always holds. And there's a question about how we actually do it, and there we'll be picking it randomly. Or maybe we'll be picking it from a grid, but sort of randomly. Yes?
How the C is perfect?
Say again?
How the C is perfect? How the classifier is perfect? Is it like the true error is 0?
Yeah. So the question is, how do you know that the classifier is perfect? The answer is you don't. But there's some tricks which will help. All right. So here's the probing algorithm. This is sort of a data flow graph. So you start with your binary data set at the top, and then you choose some p's, however you want. And then you create some importance-weighted data sets. And then you apply your importance-weighted learning algorithm, and you get your importance-weighted classifiers. And then when you want to make a prediction with some particular feature, you get your importance-weighted predictions. And then what we're going to do is we're going to look at the transition point and say, oh, we must have passed a threshold here. So I'll predict the probability, which is somewhere in between 0.1 and 0.5. Right? So maybe 0.3. Yeah? No, you don't. Yeah. I'll get to that in a minute. Do you have a question?
Yeah, this is basically just revising the line between 0 and 1, maybe
Yeah, so these numbers here discretize the line between 0 and 1. There's a question about how you want to choose your resolution and so forth. It varies a bit. Yeah? Yeah, that's exactly the right question to ask. It's the same question as here. Okay, so there's a few problems with this technique. Right, so maybe we actually want to reduce all the way to binary classification, but I just told you how to do that, right? So we can take importance weights and we can turn that into a binary classification using rejection sampling. And maybe, okay, so this is kind of a interesting point. So for the costing reduction, I said, look, you really want to rejection sample multiple times. But for the probing reduction, you don't. It's preferable to choose more P's over rejection sampling multiple times, right? And so this general principle, if you can figure out how to do it right, getting a little bit of information from a lot of places is better than getting a lot of information from a few places. Right, so how do you deal with this issue that the classifiers are not very good? So the way you deal with it is you sort the predictions until you actually get something like this. So if you get 1, 0, 1, you sort and you get this. And you just pretend that this is what your classifiers predicted. And there's a question about why that's right, but it turns out that that's exactly the right thing to do. And then there's this issue of how you discretize on P. You can do it with a uniform grid, but if you're in the transductive setting, where you have a bunch of unlabeled data that you want to predict the probability of, the probability of the label of, then you can actually do it on demand. So you start out making you choose P equals 0.5, and you see how much of your data ended up on this side versus that side. And then you can discretize to optimize your squared error loss. Okay, so this looks easy, but all the magic is happening here because I'm telling you precisely how to cope with errors, right? So how well does this work? So here we actually compare with a lot of different techniques for making probabilistic predictions, rather than just comparing with other reductions. All right, so we have a bunch of data sets here. And these are drawn from many different locations. Some of them are UCI, some of them are these KDD championships. Yeah, I think it's a combination of those two sources. And then you can look at the squared error, so smaller is better. And you can compare several different approaches. So one approach people use is they run a support vector machine on their data set, and they fit some sort of sigmoid to the margin. So the margin itself gives a pretty bad probability prediction. And there's no reason why it should give a good probability prediction because, well, it's not supposed to be a good probability prediction. They don't optimize for that. But if you fit a sigmoid to the margin, it actually comes out reasonably well. So that's what this SVM plus sig is, and that's the first blue line. And then you can run this probing technique on top of just the support vector machine. So that's what the second blue line is. And then for the red lines, you can run naive Bayes, which just makes a class probability prediction. Or you can run naive Bayes and then fit the sigmoid to the margin that naive Bayes tells you. So that's this one. And then you can do probing on top of naive Bayes. Okay, so that's nice. And then you can have a decision tree, and you can just tell a decision tree, tell me a probability, right? And it will tell you the vote at the leaves, or maybe some sort of modified vote at the leaves. Or you can tell your decision tree, you can run this bagging technique on top of a decision tree. So how does bagging work? The way the bagging works is you take your data and you sample with replacement from it the same number of times as you have data. Right? So you get a data set of the same size, but it'll only have about 2/3 of the data, and there'll be some duplicates. Then you can run your decision tree on this, and you can repeat this process many different times, and then you can look at the vote across the different classifiers that you learn to predict some sort of probability. Now, in general, this is like the margin. It's not this vote doesn't tell you the probability. Oddly enough, it works pretty well in practice. And then you can run this probing on top of C4.5. We've also done experiments with logistic regression, which turned out to be much like support vector machines. So if you look at what the smallest thing is here, it's often probing. In particular, probing on top of C4.5. So it's a bit hard to see everything because it's far away and the differences aren't too large. But it turns out that it works a little bit better than everything else on the set of tests we did. The closest competitor is actually C4.5 with bagging. So C4.5 with probing was the best, and then C4.5 with bagging, and then I don't know, a few others won occasionally. There was a question?
It doesn't look like those differences are significant.
Yeah. I mean, what this graph should tell you is that the approach is sane, right? And I will tell you personally that there was no throwing away data sets where this didn't work, right? So we just kind of, we picked them, we ran the data, we ran it, and this is what we got. Yeah. So the approach is sane. It works. Maybe it has a slight edge. Maybe not. It's not really significant. Okay, so the approach works. Right. So there's this trick we're going to use throughout the rest of this lecture, which is that for the analysis, it's extremely convenient to analyze only one classifier, or to analyze the case we reduce to only one classifier. And it turns out any time you have a bunch of parallel calls to different classifiers, you can think about them as one classifier. So the way that you do this is you just think about taking all of your parallel calls and unioning them together or concatenating them together. So concatenating all the data sets together. And then the measure that you'll be learning with respect to is sort of the union or the concatenation of the measures, or the mixture of the measures. And then you can think about running your learning algorithm on this concatenated data set to get one classifier. So the little trick you have to do is you put the name of the classifier inside of the feature space. It's not clear you want to do this in practice. We actually have not experimented with it very much. Typically, we just run one different classifier for each choice of P, right? One different learning algorithm. But theoretically, at least, you could just run your learning algorithm once with the name of the classifier embedded in the feature space. And then once you have this one classifier, you can get all your old classifiers by just, putting in the name. So this is a trick to take many different parallel calls and turn it into one call. This trick is theoretical at the moment, there have been no experiments one way or another about how well this works in practice. So what this trick means is that you can think about drawing from the distribution that C is going to be evaluated on. So you're going to use C multiple times, and that there's some particular measure over how you use it. And the way that you draw from that measure is you draw from your original distribution, and you draw maybe uniform randomly from P, and you evaluate, right? So that gives you some distribution over X cross P. Or X cross P cross Y, which is hidden when you evaluate. So this is a basic trick that we're going to use over and over again. Is it clear? Yeah?
Once you get the classifier C, do you train again?
Once you have the classifier C?
Yeah. Again, are you going to train the classifier again?
No, there's no. All the training happens here. And in particular, all the real training happens inside of A, right? So we're going to be reducing to importance-weighted classification, and then importance-weighted classification to just binary classification. And then at the level of binary classification, we just run A. And everything happens, all the training happens in this step. Okay, so there's this trick. This trick is mathematically convenient. Its motivations empirically are unclear at this point. Maybe we want to, maybe not. Let me tell you one reason why we might want to, and one reason why we might not. One reason why we might want to is that this algorithm is computationally intensive, right? You're running the learning algorithm multiple different times, and that takes a bit of work. Yeah, so if you just run the learning, if there's a way to run the learning algorithm once, then maybe you can get the same result, but perhaps much cheaper computationally. Oh, and a reason not. So there was this issue of preserving independence, but it's actually probably possible to cope with that. Instead of taking the actual union, you can just subsample from the union in such a way as you preserve the independence. More worrisome is maybe by augmenting the feature space, you've made the problem harder. Possibly. So you need to think about that a little bit if you decide to actually do exactly this. Okay. So there's a theorem. The theorem is actually kind of nice. It says for every classifier, so the classifier is taking this feature space across the name and predicting one bit. For every distribution on x cross 0, 1, this is what you wanted, right? This is the probability of y equals 1 given x minus our prediction squared is bounded by something. And that something is, okay, so we have some distribution, and we have this process of picking a p and then evaluating a c, which gives us a new distribution over binary problems. So this is the name of the new distribution. Okay, so this is a distribution. So we have the error rate with respect to that distribution minus the minimum error rate that's possible. So if I just talked about error rate, this would not be a convincing theorem. The reason why it would not be convincing is because the problems that I've created are inherently noisy. So we have to subtract off the error rate due to the noise. And then the theorem tells us something interesting. So it says that this quantity here is a regret, right? It's how good we do minus how good we could do, which is a regret. It says that if we have a small regret with respect to for this C, then we have good probability estimates. So this is kind of cool because we can't actually observe this. We can compute this, and we can compute this, but we don't know this, and we don't know that. But nevertheless, minimizing this is equivalent to optimizing that. Yeah?
Repeat how you generate the data set S.
Right. So all that I said was we have all these S sub P's, which have the importances. For each S sub P, we add the name into the feature space, and we concatenate. Yeah. Doesn't matter for the theorem. Yeah, that's how you might want to do it in practice. But they're equivalent as far as the distribution that's induced. So this process and that process up there induce the same distribution over samples that you evaluate your classifier on. The only question is whether or not the training set is actually independent. So preserving independence, if you're actually going to do this in practice, you probably want to try to do something like this. Good point. Are there any other questions? Okay, so this theorem is a little bit less trivial to prove. Right, so here's a pretty picture. And what does it tell us? So the importance-weighted loss of predicting importance-weighted loss. So when the actual answer is 0, the importance-weighted loss of predicting wrong is like this red line. And when the answer is 1, it's like this blue line. And it will turn out that when you have a convex combination of 0 and 1, when the probability is actually something between 0 and 1, the loss is also linear with respect to whatever the actual probability is. So this is actually the way the proof works, just in a picture. So it'll turn out that if the actual probability is 0.5, then the importance-weighted loss you suffer by predicting wrong here much. And then because we had that sorting step, so the way that we prove this, since there's no IID assumptions or anything like that, the way that you prove this, you say, look, let's suppose we have an adversary. The adversary controls the classifiers. The adversary has some budget of importance-weighted errors he can make. And then the question is, how far can he shift us off from the actual probability? So if his budget is equal to the area of his gray region, this is exactly the worst-case error mode. So he wouldn't err over here because since we sort, it's just going to cancel with an error over here, right? So that would accomplish nothing. That would make negative progress for the adversary. And he wouldn't err over here because he pays a large importance to have the same effect as an error here. So the way the adversarial classifiers are going to err to induce the most shift away from the actual probability is by starting with errors for the p's very near the real probability and kind of filling in everything. So that's the most efficient error mechanism for an adversary. And because that's the most efficient error mechanism, we're actually going to get the theorem. Because this is something which is rising linearly, and this is the integral of x, which is going to give us an x squared, which is exactly the squared error that you observed in the theorem. Right. I'm not certain this is clear yet. We'll come back to it. Let's try to do the math. Okay, so first claim is that the expected importance is a half. And the reason why the expected importance is a half is because you're integrating this triangle here. Right? And so the integral of x, or the integral of 1 minus x from 0 to 1, is a half. So with respect to the distribution, which draws from D and then draws from P uniformly, just have that half. Okay, so because we know the expected importance, that means that we can sort of analyze just the importance weighted problem and then multiply by the appropriate constant using that costing theorem. Right. Okay, so we have our regret here. And this regret, just expanding the definition, is so that factor of 2 is just 1 over the importance. So don't worry about that. Just bookkeeping. So we have the expected importance weighted loss minus the minimum of these two values. The best classifier would predict according to the minimum of these two values. Okay, so there's a little trick here. What we do is we say, we just change our expectation, right? So we think about drawing from x and p and then drawing from y given d of x. Drawing y from d given x. Okay? And then we can think about sort of fixing x and p, and then we can do the analysis with respect to that fix x and p. And then at the end, if the analysis holds, we can just take the expectation over x and p. So if it holds for all choices of x and p, then holds for an expectation over the choices. Right? So at that point, we can just kind of ignore this quantity. Then there's this question about what is this inner thing? So there's two possibilities. Either C is going to predict according to the minimum of these two, or it's going to predict according to the maximum of these two, right? So either suffer the minimum of these two losses, importance weighted losses, or it'll suffer the maximum of the two. So if it's the minimum, then it's the minimum minus the minimum, and that's just 0. And if it's the maximum, then it's the maximum minus the minimum, and that's this. So it's going to be that 2 times the first term minus the second term magnitude. And then it turns out that's 2 times magnitude of p minus extra probability of 1 given x. So let's see if we can see that. All right, so I guess you have a minus p times d. You have a minus p times minus d, which cancels, which means you're left with a minus p and a d. And I guess I just changed the order over there. Okay, so very simple. And now you can see that the cost of misclassification is just 2 times this p minus the extra probability of 1 given x. And that implies this line here is correct. The cost of misclassifying when p is here is that much, or maybe twice that much. It's just a straight line. Okay, so this is the end of the proof. So you have a budget of some number of errors. And then the question is, how do you use your budget as an adversary? So you want to try to induce the maximum, you want to make this probing process, make the biggest mistake it can. So the first observation is that all classifications are going to be on one side of d of 1 given x, one side of the probability of 1 given x. So it's only going to be p's that are above or p's that are below, not both. The reason why it won't be both is because when you sort, they'll just cancel out. And then the other thing to observe is that the adversary wants to make his errors for the closer p's. And the reason why that's so is because the amount the adversary pays to make a mistake here is that much, while the amount that he pays to make a mistake here is that much. So he always wants to err as close to the actual d of 1 given x as possible. So what that means is that this is sort of the characterization of how the adversary will err in the worst case. Right? So he has some finite budget. If his budget is this area, this is how he will err. Or maybe he will actually have a triangle over here. Or maybe he'll choose to err on some different problem and he'll have a triangle over here. But he has some fixed budget, and that's all there is. Right, so the adversary is going to induce some deviation delta. So it's going to be the difference between t of 1 given x and p. And the budget required to do that is this integral. So this is just computing the area of the triangle. And that's going to be, like I said, z squared over 2 times 2, which means just, delta squared. So that's the proof. Right, this says that he has some fixed budget of importance weighted errors, and that fixed budget only goes so far. It only goes this far. Are there questions about this? This is sort of the first non-trivial proof. It's not too bad because, I mean, if you just think about it a bit, you realize this is the most efficient way for any adversary, and that implies the proof. That implies the theorem. Okay, so there's caveats. One of them is log loss. Can't do log loss without making some sort of extra assumption or constraint. If you bounded things to where the probabilities are always between 0.1 or 0.9, that would be okay. And if you changed to where you didn't analyze log loss but sort of clipped log loss, that would be equivalent. But there are issues with that, because if you analyze clipped log loss, then the best prediction possible actually becomes not the probability, but something else. And this implies nothing about ranking in general. So one way that people often use probabilities is that probability of a bunch of objects, and then they sort them according to those probabilistic predictions. And then they start just running down through them and checking to see what portion each as you go through that sort. And there's no guarantees for that. Now, we actually did, of course, try and see how well this works for these things. And oddly enough, it actually works better than the experimental results are even more impressive in some sense when you use probing for these things. But there's no theory, or at least there's no theoretical guarantees. Okay, so I think it's time to take a break. Let's see. Let's take a 15-minute break. Seems good.